Let me start with a problem most of us never think about. Every time a plane takes off, a truck drives down a motorway, or even when you're driving in your car, a huge amount of energy is being wasted. Now, this is not because engines are inefficient or fuels aren't powerful enough, but it's because of something we can't see. And this is drag. Drag is the invisible force resisting motion through air. And across global transport systems, it wastes enormous amounts of fuel. Today, transport produces nearly a quarter of global greenhouse gas emissions. As a significant portion of that energy is simply being used to fight air resistance, the question becomes, what if we could reduce that resistance without redesigning engines or completely rebuilding our transport systems? Well, surprisingly, the answer may have been swimming in our oceans for over 400 million years. My name is Jason Richards, and today I will be talking to you about what sharks can teach us about transforming transport. Sharks. Sharks are one of the most efficient swimmers on the planet. They move through water with remarkable speed and stability, not just because they're powerful, but because their skin is engineered at a microscopic level. You see, shark skin isn't smooth. It's covered in tiny rib structures called denticles. These microscopic grooves channel the flow of water along the body of the shark, reducing turbulence and minimizing drag. In simple terms, they help the shark move through its environment with less resistance. So a fascinating question for engineers is, what if we could replicate that same structure for vehicles moving through air? Well, using a concept called biomimicry, learning from nature's designs, scientists have developed surfaces covered with microscopic riblets, tiny V-shaped grooves only about 50 micrometers high. To give you an idea of scale, 50 micrometers is roughly half the size of a single human hair, which is pretty small. When air flows over these riblets, the grooves help control turbulence in the boundary layer, which is the thin layer of chaotic air close to a surface. The result? Less wake, less friction, and significantly less drag. In optimal conditions, these riblet surfaces can reduce drag by up to 10 to 12%. That might not sound dramatic at first, but in aviation, even a 1% efficiency improvement can translate into millions of pounds in fuel savings and major reduction in carbon emissions. And this technology is already beginning to appear in the real world. Aircraft manufacturers and airlines, including innovations by Lufthansa Technik and BASF in Germany, have begun testing shark skin-inspired surface films on aircraft. The results show measurable fuel savings and lower carbon emissions. But here's the exciting part. This technology doesn't only apply to aircraft. It can be scaled up and applied to cars, trucks, ships, and even wind turbines. Essentially anything moving through air or water. A microscopic change in surface texture could improve efficiency across entire transport systems. Now let's look at the hard data, because in engineering, numbers are the difference between a compelling theory and a measurable impact. Since Lufthansa Technik introduced AeroShark technology in 2022, the results have been promising. On a single Boeing 777 cargo plane, this microscopic film reduces fuel consumption by about 1.1%. Now, that might only sound like a minor improvement, but for a single airline fleet of 11 cargo aircraft, that translates to an annual saving of over 4,000 tons of kerosene, or jet fuel. That would save roughly 12,000 tons of CO2. That is the equivalent of 48 cargo flights from Frankfurt to Shanghai, and effectively erasing their entire carbon footprint before they even touch the runway. That is the power of a microscopic change. If we scale this 1% improvement across the entire global aviation industry, besides the cost saving from using less fuel, we are looking at saving over 10 million tons of CO2 every year. That's not just a marginal gain. That is the equivalent of planting 450 million mature trees, roughly half the size of Belgium. So what happens next? The challenge and opportunity now is scaling this innovation. First, continued research and development is needed to refine riblet designs and materials, ensuring they are durable, cost-effective, and easy to apply across different sectors. Second, we need more projects and partnerships with transport manufacturers, fleet operators, and energy companies to test these technologies in real-world environments. And third, we need investment and collaboration to cost-effectively bring these solutions out of research labs and into everyday transport at scale. Because when you apply small efficiency improvements across millions of vehicles, planes, and turbines, the impact becomes enormous. Reducing drag by just a few percent across global transport could mean billions of liters of fuel saved every year, and a significant reduction in carbon emissions. If a microscopic groove on a shark's fin can save millions of tons of CO2, what other world-changing solutions are we currently ignoring just because they're too small to see? The future of sustainable transport won't just rely on one solution. We will need new fuels, new engines, and new technologies, but sometimes the smartest innovations isn't about reinventing the system. Sometimes it's about learning from nature and helping the systems we already have work more efficiently. If sharks could solve the problem of drag millions of years ago, then now it's time for us to learn from them. Thank you for listening.